And okay, thanks a lot for the invitation. And so just to mention this, so I did indeed my PhD in loop quantum gravity. And over the years after, I went back to more like classical general relativity. And what I'm going to present is mostly classical, okay? But it has some interesting impact on the way we can think of quantizing gravitational mini-superspace. And what I had in mind is mostly to give you some general idea, a kind of lecture on some technique to identify and classify symmetries of gravitational mini-superspace and how you can use this to try to construct some duality with other systems, and in particular with fluid dynamics. And as you can see from the title, there is a word toward, which means that the hydrodynamic interpretation that I have in mind is not yet obtained. Okay, so that's work in progress. So I will try to show you how it works. And everything that I'm going to say is based on these two articles for which I gave the archive number. And also the work that I will present has been done with Etera Levin, so from Lyon here. Daniel Oriti, one student Goffredo Piani, and another student Alexander Gercher. Okay. So so that's the main, the outline of the talk. What I have in mind is to present what we call the geometrization of mechanical system with what, and the approach is known as the Einsenhart-Duval lift. And I would like to present this in detail and how it works. I would like to give you some concrete example on some very simple system. And then how this can be used to reveal hidden symmetry of mechanical system, and in particular gravitational mechanical system. And then we will apply this to cosmology and black hole. And I will discuss how we can think of this as a starting point to build a dictionary with fluid mechanics. Okay, so let me just, like this. Okay, so let me start with some very general motivation. So as you know, one of the main challenge for today and for the coming decade is this quest of understanding and building a well-defined and predictive theory of quantum gravity. So the starting point to think of this is that in the IR behavior, the infrared behavior of the gravitational field point toward the thermodynamical interpretation. And by this, I have in mind that objects such as black hole, but also cosmical horizon, and also a causal diamond, they exhibit an entropy that you can define and a temperature. And from this point of view, you might want to understand this system, this gravitational system, as many-body system, which would be built from a collective behavior of microscopic degrees of freedom that you don't know yet, okay? And in order to identify these microscopic degrees of freedom and build the theory of quantum gravity, there have been many different attempts which have been used, that have been using different starting points. So we are not going to be interested in one specific approach in this talk, and everything that I'm going to say is based on the IR behavior of the gravitational field. But let me still say this 2 points. So there's two key challenges from my point of view. The first one is to identify the nature of these microscopic degrees of freedom. And obviously you have many different choices to encode them, okay, that give you different type of theory. And the second important challenge is, even if you have identified these microscopic degrees of freedom and you have, for example, the notion of quantum geometry, one important challenge that you will face is to understand the emergence of classical geometries from such microscopic description. So the main takeaway message is the following. So the important point to understand is that even if you have different way to encode the microscopic degrees of freedom depending on the chosen model or theory, you might expect that the dynamics of this microscopic degrees of freedom and the emergence of the space-time in the continuum hydrodynamical approximation of the would-be quantum theory of gravity to be governed by universal symmetry. And from this point of view, the task is to first identify all this universal symmetry. So the question from this point of view is how to systematically search for this symmetry in the classical theory. And okay, and if you have questions, feel free to interrupt at any time. Okay, so what we will do in this talk is to focus on the simplest case, which are symmetry-reduced gravitational system that you obtain by imposing homogeneity. So the most simple case is the 1D system where the gravitational field, so the metric, is homogeneous with respect to 3 of the coordinates. okay, that give you basically a 1D system. So this is typically the case for cosmology and static black hole, let's say. The point is that even if you are dealing with very simple systems such as 1D system, there is already some highly non-trivial challenge when you are trying to quantize this system. And the most well-known one are the cosmical phase space. Okay, and when you try to quantize this gives you then you face the problem of understanding quantum cosmology. So the interesting point about quantum cosmology is not per se doing physics with this, but really it's that it encapsulates most of the challenge toward understanding what should be a generally covariant formulation of quantum mechanics. Okay, and this is actually the main interest in studying quantum cosmology, at least from my point of view. So the first goal of this talk will be to present an approach to systematically identify and classify the symmetries of the gravitational mini-superspace, and have in mind both cosmology and black hole mechanics. The second goal is to introduce the main idea on the perspective that this work, so identifying this symmetry, open when you try to preserve this symmetry at the quantum level, and in particular in order to build dictionary with other interesting many-body system. Okay, so let me start with the geometrization of a mechanical system. Okay. So the general setup will be the one of symmetry reduction, okay, down to 1D system. So we consider mini-superspace of general relativity defined by restricting the space-time metric to a specific ansatz with a finite number of components. And by this, I mean that I'm allowed to vary in terms of chosen coordinate while the rest of the metric is held fixed and considered as background data. So concretely, you start from a metric of this type, okay? And you see that here I have the lapse n, which depend on the time t, and the induced metric gamma ij, which depend on different field, chi, which depend also on t. And you can have some dependence on x. For example, if you have spherical symmetry, you will have this sine square of theta, okay? But this is fixed. Okay. So from a more general point of view, if you do this, what you will end up with is a 1D system after symmetry reduction. And in particular, you allow the gravitational and the matter degrees of freedom that you denote by chi collectively to depend only on the time t. And if you implement this symmetry reduction in the Einstein-Hilbert action of general relativity plus the matter sector, you will end up with an action which is typically given by this one, okay? Where this is the kinetic part and this is the potential part. And you see that you have n the lapse, which enter as always like this. And LP is the Planck length. Okay. Oops. So the important point is that this prefactor C, LP, come from the standard 1 over LP square and the factor which is proportional to this factor in front of the Einstein-Hilbert action. The second point is that when you do the symmetry reduction, obviously you are integrating over some fixed region of space-time, of space. And in particular, there is something hidden in the C number, which is the 3D volume V0. This is a fiducial volume on which you restrict the spatial integral, okay? So what you should really have in mind is that when we think of this action, we are really taking into account just a fixed region of space-time, okay? And the point is that this C, which contains the V0 volume, the fiducial volume, and the Planck length is actually playing the role of the ratio between the UV and the IR scale of the system. Okay. So now this system is reparametrization is invariant at the reparametrization of the time coordinate. Okay. And in particular, you can make this reparametrization of the time coordinate, okay, where you change t, you reparametrize t, you reabsorb this, you change the lapse like this, and the degrees of freedom remain the same. Okay. So this means that at the Hamiltonian level, the Hamiltonian will vanish for this system, okay? And you can write the Hamiltonian like this, okay? So I call it small h here. So the important point, sorry, and I come back. This metric is called the supermetric, okay? So this is what we call the superspace. Okay, and as I said, the Hamiltonian is 0 in this case. When you vary the lapse, this is what it gives you. And this is the crucial feature for any relativistic system. So this keeps track of the fact that you started from general relativity. Okay, so now what we will do is try to understand how we can analyze the symmetry of this system. And to start with, we will focus on the system that have zero potential. Then we will see how to add the potential. Okay, we start from this action that we can rewrite in the Hamiltonian form like this, okay, where P is the momenta for chi. And then what we want to consider is basically all the conformal killing vector of the supermetric, okay? So which satisfy this equation. And in this case, we know that this guy will be basically a symmetry for any null geodesic on this metric, okay? That will provide some conserved charge. So in order to see this, you can construct, so if you identify, I give you this metric, you identified one vector of this which satisfies this equation.
Sorry, we have a question.
Yeah.
Yeah, I'm sorry. I just wanted to ask to the extent that about the applicability of all of this, you start gluing space-times together still within GR, but when the dynamics comes from actual gluing, something like the thin shell formalism. And in this case, the action you can still go to mini-superspace, but I think the action will not be polynomial in the momenta anymore. Just want to ask whether you have a picture for how this relates to the original part in the road that you started with, assuming really something that you sum over globally hyperbolic spacetimes and whatever. But if you do this gluing, is it in any obvious way related, or aren't you allowed to do it?
So usually, I mean, at least from what I know in the literature, we really I don't know any paper which is studying like the gluing of different region, but when this is completely symmetry reduced. So I don't know how this like junction condition will go through this symmetry reduction.
So, but you would say in a sense the safe thing for sure is to use reparametrization invariance, and then once you know the Hamiltonian is actually zero on shell, you can interpret this as a type of phase-space integral, no matter whether it actually comes obviously from the purely gravitational part in the world. So you would agree on this, probably.
I would say I agree with this, but I'm not sure I see exactly what you have in mind. I mean, what you want to do with this.
Okay. So let me
maybe you can
just
precise.
for the sake. Yeah, we can talk later, but thank you.
Okay. Yeah, okay. So what I was saying is that, okay, so you start from a system like this, which has zero potential. So you read the metric from the Lagrangian, you find some conformal killing vector of this supermetric, and then you can construct this charge, okay, on the phase space. So this is the standard charge that you would construct for a geodesic motion, like a null geodesic on the supermetric. And then you can really directly check by direct computation that this guy is zero provided H is zero, okay? So for null geodesic. Okay, so this means that this O psi associated to the conformal vector psi that you found is a weak Dirac observable of the system. So it is conserved along classical trajectory, and as a conserved charge, it will generate a symmetry of the mini-superspace by the Noether theorem. Okay, so you're happy with this. This is kind of very direct to do, but when the potential is zero. So the limitation of this is the following. So you can list all the conformal killing vector of the field space metric JIB, so the supermetric, and you will get some set of symmetry of the mini-superspace model. Now the problem is that this will only reveal a subset of the symmetry of the system, and you might miss some of them. So for example, the observable constructed above, so the O psi that I introduced just above, they will be in general linear in the momenta P, okay? Sorry. The point is that you might have some other symmetry that are generated by higher order charge in the momenta. So typically quadratic in the momenta or cubic in the momenta. So the method that I just explained clearly misses conserved charge of higher order in the momenta, and I will show you how to get this. So the second point is that this approach cannot produce what we call time-dependent conserved charge. So in other words, what we call evolving constant of motion. So typically, if you kill these two terms, okay, you have what I mean what you know, so some observable that commute with h. But in principle, you can add this term, okay? Like even if O depend on time, if it depend on time such that these two guys compensate, this is still an observable, I mean conserved charge, okay, with respect to tau. And in general, the method that I just presented will miss this kind of charge, and they are actually quite important. Okay. And the reason for this, if you think of it, is that if you try to solve this equation, psi will never be able to depend on tau. Okay. So you need to find a way to have vector field which live in an extended space. Okay, and for this, okay, as I was saying, you need an extended formalism to capture possible hidden symmetry of higher rank and also evolving constant of motion. And this is where comes what we call the Einsenhart-Duval lift. And this is basically one of the main points of this talk, trying to give you an idea on how it works. So you start from the more general system, 1D system, okay? So now we have this potential, and we have gauge fix it by fixing n to 1, okay? So we're absorbing basically n to tau. So despite this gauge fixing, we'll keep the Hamiltonian constraint in mind, and we will in particular demand that h is 0, okay? So the main idea of the Einsenhart-Duval lift is the following. You will introduce another variable u, and you add a factor u dot square in front of the potential, and this will allow you to basically construct a geodesic Lagrangian even in the presence of a non-trivial potential. So how does it work concretely? Basically, I give you this Lagrangian, okay? So you read the potential, you read the supermetric, and you construct this metric, okay? So here, this is the standard superspace. You see that the coordinates are the field, the dynamical field. The potential appear in front of a term which is du square. So we introduce two new coordinates, u and w, and we have the cross term which is this 2 du dw cross term, and you have this additional term which take into account the potential. And then what you can show is that the lifted action, which is defined as an integration over the parameter lambda, will actually contain the dynamic of your initial system. Okay. So this construction is quite old, and it was introduced by Einsenhart, I think, in the early 1930. So it's very old construction. And the point is that this formulation really look very much like the original Lagrangian. And in fact, if you take it will take the very same form if u dot is equal to 1. Okay, so if you identify u to the proper time tau. And this is actually precisely the role of the extra coordinate w, for which the equation of motion will impose that u dot is indeed a constant on shell. So let's see exactly how it works. So we started with a given mechanical system, okay, with potential and this supermetric. You construct this metric, which is a canonical construction. And then the important point is that this metric is actually the metric of is a subcase of a PP wave that we call, so for parallel plane wave with parallel front wave. Okay, and so this is typically a solution of the Einstein equation. Okay. And it has some important property. So in particular, if you think of this, you consider this vector as what we call a covariantly constant null vector. So basically it satisfies this equation. So you see this is, if you symmetrize, this is the equation of a Killing vector, but it's actually more, this is stronger. Okay, and this will be important in what follow. So as I was saying, so this lifted metric is very similar to a PP wave on that. And you have these two null direction, partial W and partial U. So the group of isometry, you can first look for the group of isometry of this PP wave. And the interesting point is that, this has been known for a very long time. It is a 5D group, which is known as the Carolean group in 2 + 1 dimension without rotation. And just to mention this, this type of space-time, this type of metric actually contains some universal information as follows. So if I give you some general metric, you can consider null geodesic, And around this null geodesic, you can construct what we call the Fermi coordinate, which are basically the coordinate which allow you to encode the leading tidal effect that the photon will see around its geodesic. And what is quite impressive and what is known as the Penrose limit is that you have a process to show you that at leading order, what the photon will see is always a metric of this type. Okay. So this is why it has been used a lot in general relativity in many different areas. And it is still used now, for example, to compute quasi-normal mode or, okay. So just to mention that there are some link of this type of metric with other area of general relativity. Okay. So now, the main point is that the classical trajectory of the system we started with, so the mechanical system that we introduced from the start, are actually the null geodesic on the lifted metric, which is given by this lift. Okay, so that's the main point. So you can compute, to see this, you can compute the canonical momenta, so for the coordinate u, for the coordinate w, and for the dynamical field chi, a. And you have this geodesic motion, the Hamiltonian for the geodesic motion on this Einsenhart-Duval lift is given by this Hamiltonian. Okay. Now the point is that if you focus on h equals 0, you will focus on the null geodesic. And the whole point, the statement, what has been shown is that the dynamic which is of this null geodesic on the lift is actually reproducing exactly the Euler-Lagrange equation of the Lagrangian you started with. So this is a very simple way to geometrize a dynamical system. Okay. Okay, and then you can compute the different equation of motion, okay, which are given like this for all the momenta and the coordinate u, w, and chi. Okay. And you see obviously that this guy is a constant of motion. Okay. So first, the coordinate w is cyclic. Okay, you can check that it doesn't appear here. So it is cyclic, which means that, as I said, pw is a constant of motion. So we can set pw to 1, for example. Then the lifted Hamiltonian, so h, the h curly, will be related to the Hamiltonian of the initial system by this relation. Okay, but since we focus on h equals 0, it means that basically you will have this relation. Sorry, this relation. So h is given by this. Okay. So okay, so that's the different projection rule when you want to project the dynamic on the lift to the dynamic of the original system you started with. And finally, what you have is that starting from this, the variable u can be identified with the original time coordinate tau. Okay. So in particular, you can deparameterize the equation of motion of the lifted system in terms of u and recover the equation of motion of the original system. So typically, you can obtain the equation of motion, the Hamiltonian equation of motion for chi and p. And you recognize that the Hamiltonian equation of motion of the original system that you started with. Okay. So the main point is the following. So the geodesic equation for a massless test particle on the lift metric that you just build canonically from the Lagrangian reproduce the equation of motion for the initial mechanical system. And you have some projection rule which allow you to go from the dynamic on the lift to the original system. And I just sum up what they are like this. Okay. So PW is 1, but it could be just a constant. Okay. I just said 1 for simplicity. And PU is minus h, and U is equal to the proper time tau, is identified with tau. Okay. So do you have question at this level? No? All good?
So maybe could you briefly explain again why this this coordinate change here is useful with the Einsenhart-Duval lift? So
the idea of the lift, if you sorry, the idea of the lift, yeah, here. So initially, we were able to, so I give you some mechanical system which has 0 potential. You just have this, okay? Then it's quite easy to understand that here you have a metric, and you can look for the symmetry of this metric. And they will give you some dynamical symmetry of the system. But the point is that in general, you have a potential. Typically, you take the harmonic oscillator, you have a potential. and this does not work anymore. You cannot do this anymore. So the question is, how do you include this potential? And in order to do this, you can construct this canonical metric starting from this Lagrangian. But for this, you need, this has been shown to, to be what you need basically to introduce the potential. You need this extension of two-dimensional extension of the superspace. So you see here we had 2 dimensions. And it turns out that if you want to have to think of this as to think of the Euler-Lagrange equation coming from this Lagrangian with V as a null geodesic, the only way to get this is by constructing this metric. So that's kind of like the extension of the geometrization that the superspace was providing for the system with potential 0. So the Einsenhart-Duval lift is really the extension of the superspace, the natural extension of the superspace.
Okay, thank you.
And you see that basically what was missing here is really taking into account the time and its conjugate momenta. So you see, U will be the time at the end of the day. So we are treating, by introducing U, we are treating the time just as other dynamical field. Okay.
Thank you.
So, okay, now we can think of, redo what we did for the superspace, and we can try to study, the symmetry for the Eisenhart lift. So what we are going to do is to look for vector field X, which are conformal Killing vector of the extended metric now. Okay. So the extended metric has this form. So here, this is the potential in the UU component. The GW, UW, the cross term is 1. And this guy is just the superspace metric that we have. Okay. And now we look for the symmetry that we can, generator of the symmetry can have this form. So before we just had this guy, okay? Now it has some extension. And this is what will give us what we need. Okay, so if you write this equation exactly, you get this system of equation. And you see that this guy is nothing else than the last equation is nothing else than the conformal Killing vector on the superspace. Okay. So no, as I said, the component of the vector X can depend on the U coordinate and the W coordinate. And if you remember what I said initially, if I was just focusing on the conformal Killing vector of this guy, I could not get evolving constant of motion. So constant of motion will depend on tau, on the time. But no, because this guy can depend on the U coordinate and the W coordinate, I will have this possibility. Okay, so now we proceed as before. We construct this guy, this conserved charge for the geodetic motion on the extended superspace, so the lift. And you can check again that this is indeed 0 on shell. So I recall just to recall the projection rule that we use. And if you do this, what you will obtain for an observable coming, which is associated to vector field X, you will obtain something like this. So here, the point is that you have a PW, but PW is 1. Here you have a PU, but PU is minus H, and this is why you get this, okay? Okay. So now you can show that if you assume that X is, because on the lift, you have a Killing vector, which is partial W, you can always focus on the observable, which are independent of W, okay? And in this case, if you solve these this additional constraint on top of this conformal Killing equation, you will find that this is indeed an observable for the initial mechanical system you started with, where H is the Hamiltonian for the initial system. So the important point here is that the method produces, as desired, the evolving constant of motion that I introduced before. So the conserved charge which explicitly depend on time, and which something which was not possible from the superspace metric. And this follows from the U dependency of the Killing vector field X that you can find. Okay. No, the important point is that in a given geometry, you don't just have killing vector and conformal killing vector. You might have additional geometric object that give you additional conserved charge. So let me show you how this works. So first of all, everything that I just said apply to any mechanical system, okay, with a potential. And if you use the conformal killing vector, what you will end up with, in general, is an observable which is linear in the momenta. But in principle, you can also have what we call a rank P killing tensor. And in this case, the killing tensor will provide charge which are of order P in the momenta. So what is a killing tensor for the one who don't know what is a killing tensor? So a killing tensor is a generalization of the killing vector which satisfies this equation. So you see that for rank 1 tensor, this is just the killing vector equation, okay? And obviously you can add something here to make it like a conformal killing tensor, but okay, that's just something more general. So this is quite important, this object, because it reveals some hidden symmetry in the sense that if I give you some space-time that has a killing tensor, in general, it will provide a conserved charge for the geodesic motion, but it will not provide a conserved charge for the gravitational system itself, contrary to the killing vector, okay? So this is in this sense that we call this hidden symmetry. So let me give you just two examples in real life. So typically the Kerr black hole has a killing tensor, which actually descends from something else that we call a killing nanotensor. But another example is the PP wave. So the exact plane wave, for example, of general relativity. Okay. Okay. So once we have constructed the lift for a given system, the idea is to systematically search for the conformal killing vector and the killing tensor in order to reveal all the possible charge that we can have. Okay. So this approach is quite useful. I mean, when you try to identify in a systematic way all the symmetry of a given mechanical system. And I will show you one concrete example of this. What I would like to emphasize is that at this level, the Einsenhart-Duval lift is a super elegant approach to basically get this non-trivial conserved charge that you usually struggle to obtain and to identify. So the evolving constant of motion and the conserved charge which are higher that are not linear in the momenta, okay, that are quadratic cubic in the momenta. Okay, let me show you one concrete example that is super textbook. I mean, okay, the system is textbook, but what I'm going to show you is not textbook. So you consider the two-body problem, okay? So, okay, this is the system of two particles in interaction with a 1/r potential, okay? And this is a gravitational or electrostatic. Okay, so this system, so the reduced system has 3 degrees of freedom. So you have R, I call R the position vector of the particle, R the distance of the particle to the center of force, P the momentum, L the angular momentum. So at this level, everything might seem very textbook, but you will see. Then this system is maximally superintegrable, is a maximally superintegrable system because, okay, the definition is that for d degrees of freedom, you should have 2d minus 1 conserved charge. And in that case, you are maximally superintegrable. So in this case, I have 3 degrees of freedom, but 5 constants of motion. The first one is the energy. The second one is the angular momentum component. The other one are the Laplace-Runge-Lenz vector, which is a quite surprising object, okay, that you have learned when you were like doing your university class, okay. The point is that out of all these guys, you have only 5 constants of motion because this is supplemented with 2 scalar conditions, okay? So A is orthogonal to L and A square related to L square, like this, okay. Now the question is, what is the geometrical origin of the Laplace-Runge-Lenz vector? I don't know if you have already seen this. So obviously what you can do is to apply the Einsenhart-Duval lift method that I just showed you, okay. So the reduced Lagrangian for the two-body motion, so for the fictive particle in this 1/r potential, is given by something like this, okay? Okay. Then you have the two momenta PR, P theta. You have the Hamiltonian, which is given by this, okay? Theta is a cyclic variable, so P theta is a constant of motion. And now you want to apply to this system. So recall that we have this guy. Okay, this is the potential, this is the kinetic part. So now we want to apply the Einsenhart-Duval lift method to the Kepler problem. So, okay, you have the du squared term, which take the which come with the potential, okay, which was minus 2v. You have the cross term du dv. So sorry, I call it v here, but it should be w. Okay, whatever. This part is just the supermetric. And we call this the Kepler lift. So now we want to understand the Euler-Lagrange equation for the Kepler motion as a null geodesic on this geometry. So first you can compute the Ricci scalar of this guy and the Ricci tensor of this guy. And you can see that this guy is not Ricci flat. So it means, first of all, that it's not maximally symmetric. So the first step consists in listing the symmetry. So it has this following conformal isometry, so a homothetic killing vector and a tree killing vector, okay, which are given by this. But most importantly, this metric has a killing tensor. It has actually 6 killing tensor. One of them is given by this, okay? Now the statement is that the Kepler dynamic is equivalent under suitable projection that I introduced before to a null geodesic on this metric. So a photon propagating on this metric. And from this, it follows that one can associate to this null geodesic a set of conserved charge coming from the conformal isometry, but also from this killing tensor. So the way to see this is that you compute, the geodesic motion on the lift. So this is the Lagrangian for the geodesic motion. You have the momenta, you have the Hamiltonian, okay? And then you compute we focus on null geodesic, so H is 0. And now you compute the conserved charge of coming from the killing tensor. And what you find is this guy, okay? So you can check that KH is 0. And then you can use the projection rule that I introduced before, which are canonical projection rule, to find the conserved charge, which is given by this. And this guy is nothing else than the conserved charge of the Laplace-Runge-Lenz vector. So in order to see this, okay, we start from this guy that we just derived. You choose some basis, okay, you have this basis or this one in Cartesian coordinate. The Laplace-Runge-Lenz vector is defined by this, okay, and you can write it in different bases, okay. And now if you compute the component of the Laplace-Runge-Lenz vector on a given direction, like in this case ux, you just end up with this, which is nothing else than k that we just derived. So at this moment, you need to stop and understand that what has been found, like this Laplace-Runge-Lenz hidden symmetry of the Kepler problem, which make it completely integrable, you can see this from a completely geometrical perspective, okay? So it comes from an hidden symmetry, which is a killing tensor object, a rank 2 killing tensor object of the Kepler lift. And you see from this point of view that this is like super powerful, because what I did, okay, let's say that we don't know the Kepler problem and you want to solve this. So we didn't have all the very smart people before us. So we need a systematic approach. And the one I'm giving to you, the Einsenhart-Duval lift, allow you to precisely identify this hidden symmetry in a completely systematic way, okay? So that's the powerful of this, the power of this approach. Okay, so that was just like a textbook example, even if this is not in any review or any, to my knowledge, it didn't appear in the literature. Okay, but it has been, there are in some review people saying that this is related to a killing tensor, but I didn't find this explicitly anywhere. Anyway, okay, so let me now just make a summary of the main point that we reviewed so far. So the Einsenhart-Duval lift provides a powerful tool to geometrize the dynamic and the symmetry which dictate the dynamics of any mechanical system. This provides a very elegant geometrical origin for the hidden symmetry of the two-body problem, as I just showed. And there are many, many different applications to other systems. So I can give you some reference on this. So what is the next step? What we want to do is to visualize the dynamic as a geodetic motion on an auxiliary space, but for gravitational system now. Okay, and in particular, we want to focus on cosmology and black hole mechanics. And what we will do is to list all the hidden symmetry of this guy using this systematic approach. So I have to say that initially we ended up doing this because we found by clever guess some new symmetry in cosmology and black hole mechanics. And we struggled to understand what was the origin of this until we found this Einsenhart-Duval lift method. And everything became very transparent using this, okay? Okay, and the long-term strategy is the following. So for a quantum system, the geodesic is basically the Econal limit of the wave dynamics. So it means that we can translate this wave dynamics into a hydrodynamic equation on the lift, okay? So using what we call the Madelung representation. And this, in particular, when you have access to this hydrodynamical equation, it opens the door to build a dictionary between hydrodynamical equation and wave function dynamics in field space. And that's the idea how you will go from finding the symmetry, geometrizing the dynamic in terms of geodesic, to quantizing this system and seeing the wave function, representing the wave function dynamics as a hydrodynamical flow on the field space. The question is, how do we characterize which type of fluid are we dealing with? And this is what we are struggling up to know to do. But there is a whole path toward this goal that we are trying to understand. Okay, so let's see how this applies to a given gravitational mini-superspace. So what I'm going to focus on is the simplest Einstein cosmology. So I will focus on flat Friedmann-Lohmet-Robertson-Walker geometry, which is filled with a massless scalar field. So the metric is given by this, and you can see that this guy is homogeneous. It depends only on t. Is homogeneous with respect to the spatial coordinate, where n here is the lapse and a is the scale factor. This is the only dynamical field. Okay, now I focus on the reduced action of the Einstein scalar system. So I start from this action, and I obtain this reduced action, okay? V0 is just the fiducial volume that I restrict, on which I restrict the spatial integration here, okay? That's the matter contribution. Phi is the scalar field, which is filling my universe, such that the expansion or contraction is non-trivial. And this guy is the kinetic part of R, okay? And you have a total derivative term that you can forget. Okay, and then it is better to introduce different variables to work out the symmetry. You have the volume V that you introduce, which is A cube. And if you do this, you get this simple action. And then it's actually even better to introduce this Z, which is square root of V. And you have to, this action turn to this guy, okay? That's just like, okay, useful rewriting of the same thing. And then what you end up with is that this system, this cosmological system, has 2 degrees of freedom, the scalar field, and Z, which is basically the scale factor. And the supermetric is given by this guy, the component. So G phi phi, GZZ, okay? Now I want to understand the symmetry of this using the Einsenhart-Duval lift. So if I apply the strategy, I will obtain this metric, okay? So you see that I don't have any potential here because there is no du square. But I could have some potential if, okay, you can do more general. So as I said, partial W, this vector that I call N, is a covariantly constant null vector. So you can compute the Veil tensor and the Cotton tensor, and you can show that they vanish. It means that this guy, this space, is maximally symmetric. And being maximally symmetric, it has the highest number of conformal killing vector. In this case, it has 15 conformal killing vector, which form the SO42 Lie algebra. Okay. So the first one, so I will first focus on among these 15 guys, I want to focus on the one that commute with the covariantly constant null vector, so partial W. So the first 3 of them are given by this, explicitly. So you see that they depend on the U coordinate. That will be the time later on. Okay. And then you have an additional 5 set of 5 vectors, which are the translation, the boost, and the rotation. And you see that they, really depend on, no, the coordinate being the dynamical field, I'm really having some symmetry which are in field space, okay? So all this symmetry will be the key symmetry that I will focus on in this talk, but there are more. Okay, so the question is, what are the associated charge of the original Einstein cosmology? Because at this level, I'm working at the level of the lift. So I want to understand this at the level of the initial system I started with, which is Einstein cosmology. So for example, let me start from this guy. Sorry, this guy, and compute the charge which is associated to this guy. So I compute the charge for the geodesic motion, and what I end up with is this, okay? Then I apply the projection rule that I introduced before. And what I end up with is this guy. So you can check that this guy is actually a conserved charge, but evolving constant of motion for Einstein cosmology. And that actually allow you to integrate directly the dynamic of Z. Because, okay, algebraically, you can just say that Z square is this guy minus plus this guy, okay? And you will find that this is actually the evolution of the volume in Einstein cosmology field with a massless scalar field. Okay, so at the end of the day, what you obtain is the following. You have this, so if you apply what I just did for one vector field, I will do it for all the five, the 8 that I show you. So I obtain that, okay, let me just show. This guy will just be the Hamiltonian, and this guy will be the dilatation, this guy will be the special conformal transformation, this guy the translation, and this guy will be the boost, and this guy will be the rotation. So if I apply the projection rule, what I obtain is this. Q plus is indeed the Hamiltonian. Q0 is indeed the dilatation in the ZP direction, phase space. This guy is the one that I just obtained. So this guy, this is actually the guy that the charge that we found in 2020 by just playing with the system. But at that time, we didn't really understood where it came from. And now we have a systematic way to obtain this. So we call this the CVH algebra because this guy is basically the Hamiltonian, so H. This guy is the dressed volume, Z is V, Z square is V, okay? So this is the dressed volume. And this guy, ZP, is actually the Hubble factor. So what we call in the old time, the Tiemann complexifier. So this is the CVH algebra, and this form a SL2R algebra. Okay, and
Sorry,
then,
if you could maybe try to come to an end in the next 5 minutes.
oh, okay, that will be short.
Okay.
Okay, so basically you obtain a set of other charge, okay, sorry, B, P plus, and J, okay. And all of these guys, they will form this algebra that is called the Schrodinger, that we call the Schrodinger-like algebra, okay. So the B and P, they form the R2 cross R2 sector. This guy form the SL2R sector, and the J here will form the SO11. So this is a boost. And since I don't have time to show you this, I will just go very quickly. So basically, just one word about Schrodinger symmetry. So the Schrodinger symmetry is basically the conformal extension of the Galilean symmetry for non-relativistic massive system. So this is the symmetry of the free particle, and this is also the symmetry of the free Schrodinger equation. Now, the important point is that this is not the only system that exhibit this symmetry. You have also a whole set of nonlinear Schrodinger equation in D dimension, which have this symmetry. And in particular, for each dimension D, you have a given nonlinearity, okay? So basically, the module of psi times psi, the module of psi up to some power, which depend on D, which allow you to preserve this symmetry. So it means that quantum fluid, which are described typically with the Gross-Pythaisky equation, they will exhibit this symmetry, okay, for a given nonlinearity and a given dimension. Now, the point is that this symmetry is also the symmetry of the compressible Navier-Stokes equation. So this suggests that if you find this symmetry, there might be a way to construct a dictionary at the level of the charge and at the level of the symmetry with a type of fluid which is living in field space. And that's the whole idea behind. The question is which type of fluid? And obviously, this will be a very non-standard one. So I don't have time to go in all detail, but here basically I just wanted to sketch the fact that, okay, how the Schrodinger symmetry show up at the level of the free particle, but I don't have time to do this. Just to show you that, okay, basically you end up, I will go quicker on this. Okay, no, let me just go. So for the free particle, okay, the standard free particle, you have a set of charge which are given by obviously the momentum, the Galilean boost, the rotation. They form the Galilean algebra. And then you have this additional charge, which are exactly the same as I showed you before. This guy form a SL2R algebra, which is given by this. Okay. And at the end of the day, all these guys form the Schrodinger algebra. The main difference is in the factor SOD. This is a compact rotation, while in gravity, what we obtain is a boost. Okay. And this is important for the interpretation. So the invariant information which is contained in this is the following. You have some Casimir for this algebra, two Casimir, S2, C2, C3, which are given by this. Okay, the details are not very important. The key point is that these guys are zero at the classical level, but they are non-zero at the quantum level. So typically, they are like a signature of the quantumness of the system. Okay, so that's a very useful way to see, I mean, that for example, when you apply this to quantum black hole or quantum cosmology, that you are dealing with a quantum system. Okay, and this is just to show you this at the level of quantum mechanics. Okay, you can introduce all these observable, okay, which are basically average observable, and all of these represent the Schrodinger algebra. Just quickly, if you add you take the quantum mechanical system, you use what we call the modeling representation, which is given by this, okay? You will end up with the compressible fluid dynamics, which is given by this equation. And this equation are invariant under this vector field, okay? And that's the realization of the Schrodinger symmetry at the level of the Navier-Stokes equation, compressible one. So there is a nice paper which explains this in detail. Okay. So the question, and I will finish with this, is what does it suggest for the interpretation of quantum gravitational mini-superspace? So the key difference is that what we obtain is a Schrodinger-like symmetry in cosmology and for black hole mechanics using the Einsenhart-Duval lift. And the point is, it has a non-compact rotation, a boost. Sorry. So where does it come from? The point is that the signature of the supermetric in 2D non-relativistic mechanical system is plus, okay? But in a supermetric for a 2D gravitational homogeneous system, this is plus minus. And that will always be the case. So it has a time instead of like being plus. And the point is that when you go to the extended phase space, so the ED lift, what you do is you add two additional dimensions, but one which is basically two null dimensions. So this is a plus minus that you add at the level of the signature. So what you end up with is a plus minus minus for the signature. So at the end of the day, what you end up with is that for mechanical system, the Schrodinger symmetry is given by this guy, so with a rotation, compact rotation. But for gravitational mechanical system, you have a compact boost. And this comes from the fact that you have two time in the extended field space, where the Schrodinger symmetry is realized. So this suggests that we can build a correspondence between a quantum gravitational mini-superspace and some type of fluid living in this, what we call a two-time manifold, so plus, minus, which is connected to other ideas that have been introduced by Barth in particular. And this suggests that this fluid can exhibit exotic relativistic and non-relativistic limit, so ultra-relativistic and non-relativistic limit at the same time. So typically, the question is whether it can have some Carolean versus Schrodinger symmetry at the same time, playing with the existence of this two time. And this would give something highly exotic to understand. So this still need to be clarified, and we are working on this. Okay, so the conclusion. So what has been done so far is, and I didn't have time to show you this, is that we have applied this to the Schwarzchild ADS mechanics. It has been also applied to FLRW cosmology, to Bianchi cosmology. It has been also used, this dictionary, to understand and explain some maps that have been introduced like 10 years ago, in particular by Litze, which was kind of a curiosity, which is a map between Gross-Pitaevsky equation and the Einstein cosmology dynamics. And this map, this dictionary that I just introduced, actually make transparent this map. Okay, What is under progress is the construction of the dictionary between the fluid in field space and the quantum gravitational system, so both cosmology and black hole. What we're also doing is to study the consequence of deforming the Wheeler-DeWitt equation with nonlinear correction selected by symmetry, just as it happened for nonlinear Schrodinger equation that preserve the Schrodinger symmetry. And what is more like a long-term goal is to construct analog avatar to be tested in tabletop experiments. So typically, you can, in analog gravity, you can reproduce using fluid dynamics some fixed geometry. And in this case, the idea would be to reproduce the field space and not some space-time geometry. And then to study the perturbation on top of this guy. So this would be a way to reproduce some dynamical system in analog gravity experiment. Okay, some open question for the one who are interested in this. Can you extend the Einsenhart-Duval leaf construction in a covariant way, so including the lapse in the picture? So this is one of the main problems of this approach. The second question is, can we extend the Einsenhart-Duval construction to field theory? Because at the level, we are dealing purely with mechanical system, and this is a high, like a very annoying restriction. And can we characterize further the type of fluid which is involved in this dictionary? Can we apply this to cosmical perturbation theory, for example? Okay, so thank you.
Thank you very much for your presentation. And think we can stop the recording now.